In this video, we're going to talk about sample means. First up, let's define a phrase called the sampling distribution of the sample mean. And you could probably guess what this means. It's how the distribution looks when you graph it out. So the sampling distribution of the sample mean, x bar, describes the distribution of values taken by the sample mean, again, x bar, in all possible samples of the same size from the same population. So for example, we've got two graphs here. It looks a lot like a previous video where we gathered a bunch of p-hats. It's kind of the same idea. So if we were finding x bar, so this activity had to do with sampling pennies that were made in the 2000s and what their years were, but you were essentially looking for pennies from the 2000s. So what's interesting here about these two distributions is that we're still looking at our same x bar, so the sample mean year, but what's different is that in this one, our n value is 5, and this one, our n value is 20. And so what is the difference between a smaller n value and a larger n value? You could probably guess, but let's talk about it, at least in these two examples. So when n equals 5, the shape, which is something that we analyze for a distribution of any kind, sample or population, this guy is slightly skewed to the left when n is smaller. But when n is larger, we get something that is roughly symmetric. You could draw a bell curve around that. And then the center is actually the same for both graphs, or relatively the same. They're around about 2002, right there, 2002. And then our variability, so the distribution of our x bar, or our sample mean, is about half as variable when using samples of a larger n value than of a smaller n value. So this one goes from a little bit more than 1995 to before 2010, and this one goes from 1990 all the way to 2012, looks like. So higher n value, you get something that's more roughly symmetric, and the center essentially stays the same, which happens in a lot of distributions, depending on the n value. And then variability becomes less variable the higher your n value. So if you have a sampling distribution of a bunch of sample means, so those are the averages of your samples, and if you have a distribution of them, how do you find the mean and the standard deviation? So first up, the mean of a sampling distribution of x bar is going to be this mu sub x bar, and that's going to be equal to mu, which is our population mean. So that's nice. And standard deviation, so that's going to be sigma sub x bar, is going to be sigma, so that is the standard deviation of the population divided by the square root of n. So in the last example, you'd either use n equals 5 or n equals 20. So the 10% condition must be met. So that means that your sample is less than 10% of your population. All right, this shouldn't surprise you. Let's do an example. So this one is called Been to the Movies Recently? So the problem says the number of movies viewed in the last year by students at a large high school has a mean value of about 19.3 movies with a standard deviation of 15.8 movies. Suppose we take an SRS of 100 students from this school and calculate the mean number of movies viewed by the members of the sample. So first up, let's identify the mean of the sampling distribution of x bar. Well, if I take the equation from the last slide, that tells me that this mean is the same as this mean. So our mean of our sampling distribution is 19.3 movies. All right, next up, let's calculate and interpret the standard deviation of the sampling distribution of x bar. And of course, let's verify that the 10% condition is met. All right, so the first thing that I'm going to do is try to make sense of that 10% condition. So we don't know the exact number of students or the entire population of students at that large high school, but we're going to have to assume that 100 is less than 10%. And that population has to be greater than 1,000 students, which if you know anything about large high schools, that's not hard to do. So next up, assuming that our 10% condition is met, let us find the standard deviation of our sampling distribution. So we've got our equation here, and I just plug in my population standard deviation, which is 15.8 movies, and divide it by the square root of n, which is 100, which makes for a nice 1.58 movies. And what does that mean? So if we have an SRS of 100 students, that means that the sample mean number of movies watched in this sample will typically vary by about 1.5 movies from the true mean of the population of 19.3 movies. So something else that happens between a population and a sample, or can happen, is that if your population is normally distributed, so for example, this curve here, that would be the population distribution. So if the population is normal, capital N, then your sampling distribution of X bar also has a normal distribution. So it might look a little bit taller than the actual population, but that's okay. It's a sample. Weird things happen. So you might be thinking, well, that's great, but what if your population is not normal with a capital N? Well, there's a couple things that we can rely on, some patterns that we can rely on. One of those is something we call the central limit theorem, or CLT. So that is when you set up a sample of size n from a population with obviously a mean, mu, and a finite standard deviation, right? You got to have those very basic things. The central limit theorem says that when your n, so your sample, is large, the sampling distribution of the sample mean, X bar, is approximately normal. So the image that you see here is you have a parent population of different sizes, different things, and what ends up happening between this parent population and the distribution of means when n is small compared to when n is larger, you can start to see that this one looks pretty normal, and then it distributes to something that is much more normal looking. And then this population ends up with a small n size here that's skewed. But when you increase the n size, you get a normally distributed or seemingly approximately normal distribution. And then this one, which is a different parent population with a wide gap in the middle, so you get this distribution of means when your n is small, and then it magically, well, not magically, but statistically becomes more normally distributed the greater your n value. So that can be summed up into these few sentences that we have here. So it's about the shape of the sampling distribution of the sample mean, which is the whole point of this video. So the first point is that, like we said before, if the population is normal with a capital N, then the sampling distribution is also going to be normal, also with a capital N. But if the population is not normal, the sampling distribution of our sample means, X bar, will be approximately normal when the sample size is large. So that's when n is greater than or equal to 30. And obviously it's going to depend on the case and what you're sampling and what makes sense for your n value. And then if the sample size is small and the population distribution is not normal, then the sampling distribution of your X bar will retain some characteristics of the population distribution. So if it's skewed to the left and you have a small n value, little n, for your sample, it's probably still going to look like the parent population. All right, one last example, 2 parts. Hang with me. This one is called free oil changes. And any of you that have a car that needs oil changes, oh, wouldn't that be beautiful? Free oil changes. Here's the problem. Keith is the manager of an auto care center. Based on service records from the past year, the time, in hours, that a technician requires to complete a standard oil change and inspection follows a right-skewed distribution, with the population mean being 30 minutes and the standard deviation being 20 minutes. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? So the first part that we're going to do is calculate the probability that the average time it takes to complete the work exceeds 35 minutes. All right, so first thing I'm going to do is I'm going to find my sample mean here of my sampling distribution, and that is 30 minutes because it's the same as our mu. And I'm going to find my standard deviation of X bar. I'm going to use this equation. Our sigma for our population is 20 divided by the square root of n, and n, or a sample, is 40 customers. Doing that calculation, that's about 3.16 minutes. That a typical work will vary from that mean of 30 minutes. So I want to find the probability that it takes more than 35 minutes. What are the odds that, Keith didn't budget enough time? So graphically, it's something like this, where we have a normal distribution, and if x bar is 35, so that's the 35 minutes that Keith has budgeted, and I want to know what this shaded area, what the probability of landing in this area would be. So thinking back to when we did all that normal distribution calculations, I'm going to use normal CDF because that's going to give me the area here, and that's going to give me the probability that, hey, Keith didn't budget enough time. So plug in the lower value of 35. The upper is something much bigger, so like 1,000. Our mean of 30 and our standard deviation of 3.16, and that pumps out 0.0568. So that means that there's about a 5.68% chance that Keith hasn't budgeted enough time for the free oil changes. Not bad. And our last question here is, how much average time per customer should Keith budget if he wants to be 99% certain that he doesn't go, quote, over budget, end quote? So if you want to think about this visually, we want to find our x bar value that will give us an area to the left of 99% or 0.99. So that we will need our inverse norm, or in the norm. And so then we plug in the area first. So 0.99, our mean of 30, or standard deviation of 3.16, which we found in part A. And that gives us 37.4 minutes. So that means that to be 99% sure that he has budgeted enough time, Keith should plan for an average of about 37.4 minutes per customer. I got nothing. No free oil changes, nothing. But thanks for watching.